and I have the audio here, if I'm not mistaken. Can someone make a test and speak from the online and to see if we hear?
Yeah.
Ah, great. Yeah, thanks. All right, we did the bingo. And first of all, I need to give you a couple of corrections from yesterday, and that was because I was giving you the wrong rules for the quantifiers. And you will see why the confusion was, and it was basically I gave you a mix of Goldblatt's rules and a mix of the old rules. So when I proved necessity of identity, I made a mistake. And thank you, Magnus, for. Oh, I'm going to put here. I went on a rabbit hole yesterday about the meaning of flabby. So first of all, these are the axioms for the frames, and then they look the same, but there was a very weird axiom here. I mean, I think it was over here that said for all x, phi, then psi, then for all x, phi, then for all of x, psi. And then I did something sneaky with it, and then I told you, no, you know what? The thing it has to be like this. Well, it turns out in the original way, this is an axiom, but not of this system. So sorry, I confused it. And also, I used a different rule of generalization. Sorry, I was mixing stuff up. The axioms of quantified K with identity plus the Parkham formula are universal instantiation, you know it, it's the common thing, vacuous quantification, we have reflexivity of identity, Leibniz law, well, NI, the Parkham formula, and importantly, we have this rule of generalization, which is what's going to allow us to show the converse Parkham formula. We start with this, which is just an instance of universal instantiation. We necessitate that with the box. We distribute the box. And then over here, we quantify using the rule gen, which was this. Before this, I only had this rule, which is not enough to prove that. All right, Magnus, I hope this answers the questions that we had yesterday and the mistake in the proof. Now,
Yes, thank you.
Why are sheeps? Why are flabby sheeps flabby? So if you missed it yesterday, this name flabby raised some eyebrows. Well, it turns out that it comes from French. This is a term that it was used in French topology. It was flasque, so it was you say this comes from French, the term flasque, and I ask around, and people are not really sure why you would call this flasque, but a French-speaking mathematician told me that you use flasque in your day-to-day to say that something is loose, like gelatin. When you shake it, that's a very bit loose. Not when bone falls off when meat falls off the bone, more like gelatin being loose. That's as far as I could find. Then some other mathematician told me, like, I don't know, but here here is a list of funny names in mathematics, but that didn't take me anywhere. So sorry, I don't know why flabby sheaves are called flabby, but you can also call them flask sheaves if you are not into this. All right. We're going to talk today about admissible models. Now, the background of this is going to be highly algebraic, but don't worry, you don't need to know a thing about algebra. The idea of this is that we don't have to understand basically what was the algebraic background of this, but you relate it to ideas that I hope you've seen anywhere, somewhere else. So let's start by saying that, well, we saw the naive approach, and we saw that with the naive approach, we have the problem with completeness. And then we saw another thing, and it was that we tried to give semantics for contingentism a la Resto, and what we found is that we could do it very nicely. So, but we need to do it with the sequent calculus. What we're going to try to do today is look at a semantics which is going to validate the contingentism without the sequent calculus, without proof theoretic semantics, but actually with a notion of semantics which changes vastly from what we've seen so far. And these are the so-called admissible models. So let's start by saying how the intuition of how are we going to interpret this quantifier right now. So what I've told you so far is that to interpret this quantifier, first you need an interpretation, and then you need
it's zoomed in on the part of the page where I can't see what you're writing.
Maybe it got stuck. Can you tell me if you see now?
No, I can't. It's I can see like text in the top left corner. Oh, wait. Yeah, no, better. Yeah, better.
And then you have a variable assignment, right? And then we have the trick in which this is true if and only if, and we did the V-varied interpretation is that every assignment that changes from this to this, it's true. That is how we do it in modal theory, normally how they teach them. But what about we interpret this in another light? And the idea of this is that we do it only as people way back did it, and we think of this as an infinite conjunction. Let's put infinite here. So the idea of this is that you say that this is true if phi x1 x and this R's conjunction is true, where all these belong to the domain, and the domain is precisely of size n. So this is a way that it is not how it works in normal modal theory and how we have it nowadays, but it is an interpretation of the quantifier that was once proposed for this. It was not very successful, but what we're going to try to do is to recover this interpretation of the quantifier to give us semantics of quantified modal logic. And then when we do this, we are going to actually see that we can make a lot of interesting stuff with this. Namely, we can have Barkan formula, but we can have models in which the converse and the identity fail. We can have identity and both Barkan formula falsified. But what we have to keep in mind is how we are interpreting the quantifier. So the idea is now we're going to be in a language, and this language we're going to call QG for quantified Goldblatt, and it's going to be a first order modal language with identity. So this has identity, and this has existence predicate, which I'm going to denote with this epsilon looking thing. We are unfortunately not going to be able to focus on this. And today we're going to focus a lot on this. If you want to do a presentation on Goldblatt, the idea is that you tell us what how does identity work here. But I'll give you the language, and then so that we can discuss stuff about identity. But know that the notion of identity that Goldblatt is going to propose is going to be a little bit different in the end. For now, you can interpret it as what you know about identity, and we have discussed. So for the syntax, we're going to have the usual thing. So this is going to be defined already as what we have, but of course we are going to make some way for this existence predicate, and then the goal is to show, our goal is going to show that this satisfies an actualist view. So what does it mean? It means that it quantifies strictly over objects in the domain such that this is true, so that they exist. So the axioms of this are going to be just a little bit different. So I'm going to give you the basic logic, so to speak. So we're going to talk about the existence. I thought I changed this. Give me a second. Weird. There's a typo, but I'll fix the notes. So I'm going to give you the axiom, the system KGK, quantified Goldblatt K. So the axioms for this are the following. First, we're going to have actual instantiation. And this is for all y, for all x, phi, then we replace every instance of x with y, and y has to be free for x in phi. What is different? So compare this with your normal instantiation axiom. So what is different between this and this? Come on, you can do it. For all y. Yes, it has a for all y. And the point of that is going to come later, and I hope it clicks. But from the time being, I want you to see that this is going to bias free logic in a very cheap way, because if we have only this, we're saying for all the objects, you can do this. But this puts a first restriction so that when you give a quantifier which only quantifies over existing things, you already know that this one is going to be only about the existing things. And then you can plug this here. Is the idea more or less clear? All right, now we have the thing that confused me yesterday, which is universal distribution, dist, which is indeed for all x phi, then psi, then for all x phi, for all x psi. Now we have it. And now we have vacuous quantification. And I mean, of course, this is an extension of K. So we have all the theorems of K. So we have positional logic, necessitation, most points. And as for the rules, we're going to have universal generalization, term instantiation, generalization on constants, and that's it. I have to check something. Give me a second. I'll check it later. All right. This is the system in which we don't add any axioms for the existence predicate. Now, the interesting happens when we include some axiom for the existence predicate and we see how far can we go with only this. So the rules that we're going to need for the system of existence quantified Goldblatt K is basically for all x phi, then if the term t exists, then yeah, where t is free for x and phi. And then as a rule, we get that if phi, then existence, t exists, and psi, then phi for all x, psi. The first interesting result actually here is that if you close the system with the existence predicate under classical logic, you can derive all the axioms that we saw previously. So just this axiom plus classical logic and this rule, which we're going to call existent universal intro, this is enough to buy you. So this we're going to call existing instantiation, or EI. So with EI plus existence universal introduction, and we close it on the propositional logic plus propositional logic, we get the actualist instantiation, we get universal distribution, backwards quantification. Let me just put this over here, backwards quantification, and closure under universal generalization. So this is because, again, the purpose of Goldblatt is to give you a quantifier that it's already free logic in a sense. So this rule, I don't know if it is weaker or stronger than the other one, but it's going to be more restrictive. So take into account that if you add this, you will not get the version of the actual instantiation which doesn't have the universal quantifier at the beginning of it. But if you add the universal quantifier, then you're going to be. So if you're into, we're not going to see the proof of this, but this is theorem 3.1.2 of Goldblatt's book. If you're interested, though, it's also cited here in the notes. Questions about this? Can you see that this is not exactly quantified, the quantified logic that we were studying before? Yes? Good. The modality here so far, it's only necessitation and decay axiom. So it's very, very bare bones. We don't have identity, necessity of identity. We don't have Barkan, converse Barkan, anything at all so far. And well, if that is good and clear, I'm going to move on to the semantics. But first, the idea of the semantics is going to be different. So from what we have studied so far. So for the semantics, I'm going to try to explain the intuition behind what Goldblatt is doing, and then I'm going to tell you how to do it formally. So the problem with how traditional semantics work for Goldblatt is that you can have this idea of, you can explain what a possible world is, and you can specify it with a set. You can say that they are a possible world is the set of propositions which are true in that world. So that means that you can, from the power set of the set of possible worlds, you can have any combination of propositions. And the idea of Goldblatt is to say, we are not going to have the full power set of the set of possible worlds. We're going to have a restricted version of this. And we're going to build it from bottom up. Normally, when we do quantified modal logic and first order logic and mix them with quantified modal logic, I tell you, you can have any proposition, we're going to be able to express it in this language. Why? Because I can give you any possible world, and then in this possible world, I'm going to construct the propositions which are true. So imagine more or less when you were in first order, when you were in modal logic, or when you were in MRM, and the professor came and say arbitrarily, oh yeah, this is a world where these things are true. This is a tool that is very useful to explain this. And then you arbitrarily set, if you think about it, this configuration is, let's call it W1, is itself something that you take from the power set of the possible worlds. You arrange it somehow so that the propositions which are true are exactly P, Q, and R. But now we're going to build it bottom up. That means that I'm going to give you a model structure, which I'm going to call, and from that we're going to start building the domain, the admissible model piece by piece. Is that more or less intuitive? Do you understand what we're doing right now? So in algebraic terms, this basically means that we're going to create the Boolean algebra of propositions. But if you don't understand what that means, don't worry. It's just to give a heads up. All right. So the idea is for when we do, I didn't already said, yeah, semantics. So the idea of this is that we move from the power set of possible worlds, and then we go and move directly into the worlds that are quote unquote expressible. Expressible with regards to what? Expressible with the regards to what I feel it with. So the first definition that we're going to have is that of a modal structure. And then in this modal structure, well, this is going to be in the language of Quantified. Goldblatt is a quintuple of world relation special set prop this is going to be sorry for the notation. So U is going to be the domain, and D is going to be an assignment function that creates the varying domains. I'll explain that in a second. So with this is just a quick frame. Now, the set prop is going to be a subset of the power set of the possible worlds. So this is a Boolean algebra of subsets of W. So what does this exactly mean? It means that when you create your model structure, you're going to give me a set of worlds. Let's say in this worlds, in here, I'm going to have W1, W2, W3, and then we are going to only take into account the subsets of the power set of the set of possible worlds which are closed under complement. So no, this is like this. And those that are under the meet operation or the conjunction. So this and this and so on. So the point of this is that when we create the range of things we can say about our objects, we only get limited to what we can say immediately in the starting possible worlds. Create arbitrary possible worlds in which you can. Oof. Sorry, you see here, you don't see online. So if I tell you that there are certain possible worlds in which some things are true and there are other possible worlds in which some things are true, you can either start saying things about what it's not in the one in either possible world, or you can say things which are in the which are true in both possible worlds. This doesn't mean that you cannot do about the disjunction, for instance, but this is the basic, and you can define the other operations under that. So we are building the model, so to say, from the bottom up. And then we're going to have U as a universe of individuals. And then we're going to have a function D, which assigns to each world a subset dW of the universe, which are going to be the individuals that actually exist in W. More or less clear so far? All right. So we're going to make a distinction that we haven't made for any of the other systems, and that is a distinction between pre-models and admissible models, or just models. But so we have a structure, we're going to have a pre-model, and we're going to have an admissible model. Why is this? Because we still, this is, so to speak, this is still modal logic, and now we're going to make it a quantified modal logic. So we need to distinguish between these two. So the first thing we're going to do is to, so let's define pre-models. And they're going to be, I'm going to write them like this. They're going to have a model structure and an interpretation. And then we're going to assign to each P, we're going to assign, so to n array P, the interpretation is going to assign something within the power set of the set of possible worlds. So how the predicate is satisfied across possible worlds. And then to a constant and elements. So the interpretation of C is going to be something in the universe. So now to define truth, we're going to use the tools that we know from free logic to interpret this, because we're going to ingrain the quantifier right now with a, well, I'm calling in the notes a proto-existence predicate. So it's a proto-existence predicate, because here we're going to have this E, which I didn't introduce in the set of symbols, because this is just a predicate. This is not a logical symbol per se. And the idea of this is that we're going to, rather than define the universal as a intersection over a domain, the truth is going to be, or the truth of the universal quantifier is going to be dependent of this. So do you remember how did we axiomatize the existence predicate in free logic? So if I say that A exists, this is defined as there is an X such that X is A. Remember this? Does it ring a bell? We happy with this? Okay. So here in Goldblatt, so for Goldblatt, this proto-existence is going to be simply interpreted as A is in the universe. So if you want it even more formally, so EA is the proposition which is equivalent to the set of worlds in which A is part of the domain at that world. So, and when we define truth, everything works more or less the same, except for the universal quantifier. So, relative to, so we need this. So, truth is going to be relative to a pre-modal and an assignment function. And then we say that so this you interpret it as the intersection of objects in the universe I'm going to write it first, and then I'm going to explain it, if that's okay with you. So what we're saying here is that this is true. It is equivalent to saying is that this is true. And what is this? What is this? It is an intersection of conditional statements. Remember what I told you about here, the universal quantifier being an infinite conjunction? This is exactly this. This is where it's supposed to pay off. So this says that you should interpret this as a conjunction of all the elements in the universe, and you say, so if there are three things, if there are three things in your universe, this is how you interpret the universal quantifier. Of course, you have domains which can have infinite things. So you have to interpret this as a conjunction of this. More or less clear? Are we good? Are we not good?
I'm not sure what the F is on the tree.
So it's going to be the assignment of things for the constants to the universe.
And it's different from the
so you have the I, which is the interpretation, right? But you can create a model of using that, and you can do it different ways, right? So this assignment is going to be so this definition is relative to this particular assignment. So you can create the first we have the interpretation, which is basically you have the functions that map them, right? This is a particular one. Yeah, I think it's the same thing. This is just like one. So the point is like if you change it to another one, you're going to have a completely different interpretation of this.
Yeah, but I'm sure how to like I thought the notation with the
the bar?
Two bars was like, is that the set of worlds where that proposition is
yes,
true?
yes.
Okay, so then how do you read the implication from like just a statement to a set of worlds?
So the set of worlds in which this is true is the same as the set of worlds in which all of this intersection is true. So
okay.
So this proposition is going to be represented by a set of worlds, right? Where the set of worlds where this is true.
Yeah.
This is another proposition, and this is another proposition.
Yeah, that makes more sense to me. It's more like above you have this, there exists a implies to like, I don't know, just
okay.
I don't know, maybe I just need to think of it.
All right, but I mean, if it does bug you,
it's just like it's an implication from a statement to the set of worlds.
Yeah. Okay. So maybe let's change this. And yeah, the point is that you should interpret this as a Boolean condition. So this is so in algebraic terms, this is an implication relative to the algebra of admissible propositions. So the idea is that, so you define this, let's use something more clear. As so bear with me. So I know you are understanding this, but so the idea is that this is not x or y, right? And this is true if this is false or this is true, right? So strictly speaking, yes, we should be using this symbol because we are describing a set of worlds, and that set of worlds is going to be the intersection in which the Boolean so in this algebra of propositions, this conditional holds. Better? Right. Okay, so this is going to be stronger than the standard Kripkean condition because in a standard model, for all x, phi holds at a world W, if for all the actual that are in that domain, it holds. But in Goldblatt, it is this is necessary, but it is not sufficient because you need it for the proposition that something is phi to be actually expressible. So let's say that the truth of every instance has to be witnessed, or you have to cover each of the instances. So this is just to say that here you need to first take a look, and in that set, there has to be the A, and then you go check if for that A, phi holds. If we had a traditional reading of this, only with the conjunctions, let's say, you only need this to hold, the second part. But now we're putting more restrictions on this. Okay. Now I want to say maybe okay, no, I'm going to make a pause. This is a great place to make a pause. And then I'll pause the recording here. We'll be back in 10 minutes. So a little bit over 10. So a little bit, at 20.